Now, we've been talking a lot about neurons and axons and axon terminals, but what's a nerve? A nerve is basically hundreds, or at least many, neuronal axons all bound up together. So this right here, this motor neuron, this nerve, is actually made up of lots and lots and lots, or well, it's actually up here. So you have a nerve overall, and you have branching of the nerves. And this is made up of lots and lots and lots and lots of axons. Could be a few, could be a few dozen, could be a few hundred. One of these motor neurons will branch off and interact with something else. If it interacts with a motor or with a muscle, it's a motor neuron. Okay? So you have these branchings of the motor neurons, and then you have axon terminals at the end here. When a neuron fires, when you have an action potential that's generated up here that gets rushed down the length of the nerve, all of these are going to engage in that action potential, and that signal is going to be transmitted evenly across all of the neurons that participated in the process. Therefore, when a nerve fires, as we say, as an action potential is generated and is transmitted through a nerve, and all the motor neurons within that nerve are affected, all the muscle fibers that motor neuron touches are also going to be stimulated. A motor unit is the combination of a neuron plus all the muscle fibers that it innervates. So here's one motor neuron, and that branches off and touches all of these individual muscle fibers. There's one axon terminal per muscle fiber. One neuron branches to multiple axon terminals. One nerve is made up of many neurons. Conversely, lots of neurons make up a nerve. A neuron will branch. One of those within a nerve is going to branch to a lot of different axon terminals. And each axon terminal is going to have its own muscle fiber, or at least its own segment of the muscle fiber where it used to be a cell in development. In areas where you have very fine motor control, like your fingertips, for example, you have lots and lots and lots of small motor units. You have one motor neuron that's only going to end up stimulating a few muscle fibers. If you have a motor neuron that branches a ton and stimulates a ton of muscle fibers, you have less precise control. So your thigh muscles, for example. You have relatively few nerves that aids in the contraction of these big, beefy muscles that don't need super fine control. You're not like writing or anything with your thigh muscles. You're moving whole, big, hefty bones. So you have a few nerves that spreads out a lot at their ends and comes into contact with lots of muscle fibers, so that you may not have very precise control, but you can generate a lot of force with one electrical zap. In some place like your fingers, you don't necessarily want your whole hand to clench up every time that you send it a signal to do something. You want to be able to pinch your fingers together, spread them apart, oppose them, adduct them, abduct them. And you want it to be able to do it with a very, very fine degree of precision. So you don't want any one motor neuron to touch any more muscle fibers than you need it to. Remember, that signal is going to get sent evenly down that motor neuron into whatever it's touching. So you want small motor units in places where you want fine motor control. Your hand isn't going to need to do any heavy lifting. Your arm can do heavy lifting, but your hand itself doesn't really generate much force. You need precision there. Motor units are spread out and don't really overlap much, if at all. So if you just cut off the motor neuron, the branches that innervate certain muscle fibers will no longer be able to communicate an action potential, and these muscle fibers won't be able to contract. But that doesn't mean that the muscle fibers over here won't be able to contract. They're stimulated by their own motor neuron. They are their own motor unit, and they can still contract. And since they're spread out and they don't necessarily communicate with one another, that preserves function. It means that damage in one place doesn't destroy functionality in the whole area. Now, as you do need to generate more force, you're going to recruit more motor units. If you have a low load, now think about your arm for a second. Just put it down on the table so that your forearm's on the table, your palm's facing up, it's supinated, and you're making a more or less a right angle with your arm. Put a pen in your hand, just a regular old pen, and go to lift your forearm, bend your arm. It's easy, right? Pencil, pen, whatever it is you're actually holding in real life, it doesn't really weigh much of anything. In this case, you have a low load, so the muscle is going to stimulate or request kind of a low voltage change. There's less voltage change because you have less force. Therefore, or less of a load, less that you have to move. You're not going to stimulate things any more than you have to. That would be a waste of energy. So you pick up this low load. There's only a low voltage change that needs to happen to pick up this light thing. And so a relatively small number of muscle fibers are recruited. You have movement in the whole muscle because muscle fibers within that muscle organ are going to be pulled at kind of randomly to contract. And so overall that whole muscle will get to contract, but only a little and weakly because you're only picking up a pencil. Now take your cell phone, which is a little heavier, put it in that hand and go to lift it. That's a medium load. That's going to induce a moderate voltage change. You need more force than you did for the pencil alone, but not much still. So you're going to pull in more muscle fibers to help you out. More muscle fibers within that muscle are going to contract. Not every muscle fiber is going to contract every time you have a contraction of the whole muscle. A low load is going to recruit some of the muscle fibers, a medium load is going to recruit more of them, and a heavy load, like if you take your whole coffee mug, put it in your hand, and then lift your arm, bend your arm, that's going to require even more of a voltage change, and more muscle fibers are going to be called into action. This is called recruitment. The larger the load, the larger the voltage change exists to stimulate contraction, and the more nerve fibers are going to be excited to contract. The minimum voltage required to create a contraction is called the threshold stimulus. There's going to come a point where you're simply not exerting enough of a load on something to warrant anything to contract. When you're sitting there with your arm on the table and you think about just kind of moving it, you're sort of sending a bit of a signal to your arm to move, but not enough to actually make it move. When you send enough that you can lift your arm, any amount, you've hit threshold stimulus. I do an experiment with a human physiology lab at a different college that I teach at, where I have students hook up a bar electrode to their median nerve, to their median nerve. And then when the median nerve is stimulated, like we send them a little electric shock, their thumb might twitch. Now, if the shock is light enough, if the shock is low enough in amplitude, your thumb won't twitch. You'll feel it, like you'll feel a shock, but your thumb won't move. And then as you crank up the force of that electric shock, you'll feel it more and more and more. Your thumb still won't move, and there will come a point where it's just going to be just high enough to actually create movement in your thumb. That's called reaching threshold stimulus. After that, so this would be threshold right here. Whatever the force was to cause that would be your threshold stimulus. Now, as you increase the amount of voltage sent to a muscle, the amplitude, the amount of force that you'll exert with that muscle will get bigger and bigger and bigger to a point. There's going to come a point where all the potential muscle fibers that can participate in contraction are participating in contraction. So then it doesn't matter how much more after that point you crank up the voltage, you crank up the electrical force, your muscle isn't going to contract more. You only have so many fibers. This is called maximal stimulus. Summation and recruitment. As demand increases, more motor units are recruited. If your muscle experiences a low amount of resistance or has to lift a low load, a small amount of weight, put your arm down on the table so that your arm is flexed. Put a pencil in your hand and go to lift that pencil. There's a load on your hand, the weight of the pencil, but it's not much, right? So in order to move that pencil, you're only going to have to change the voltage a little bit to get movement, to get enough muscle fibers to play into the process where you would get movement. So a low load warrants a low voltage change and will create movement in a small number of muscle fibers. In your muscle organ, the whole organ, it's made up of lots and lots and lots of muscle fibers, right? And they're bound into smaller subunits and whatever, but it's all just a big bundle of muscle fibers, really. When you're contracting a muscle, not every muscle fiber is always contracting. You're not going to waste energy if you can help it. You're only going to contract enough muscle fibers to do the work that's requested to be done. So you put a pencil in your hand, you go to flex your arm, you're only going to recruit enough muscle fibers to pull the weight of your forearm and that pencil up, and no more. The heavier the thing is in, for example, your hand, let's switch that out for your coffee mug. You can switch out your coffee mug for a brick. The more force, the more weight, the more lift, the more load, the more resistance that you're putting against that movement, the more that is, the more of a voltage change will be warranted or required to create more force and to bring in more muscle fibers. The process of bringing in more and more muscle fibers to do work is called recruitment. Now, there's a point where if the stimulus is too low, no movement will be created. For example, if you just keep your hand down on the table, like you were, your arms flexed and relaxed, and you think about moving your arm, you might even feel a little bit of a tug on your arm, but it's not going to move. You're not sending enough energy, basically, to these muscle fibers to cause a real contraction in the muscle fibers, to cause any of them to be induced to contract. You need to send a certain amount of energy to it to cause this to happen. In my human physiology lab, I do an experiment with my students where they put a little electrode on their median nerve, and it's going to give them an electrical shock. And you start really low, and then you crank it up a little bit slowly. And they find that when the voltage change, or when the voltage is very, very low, they'll feel the electric shock in their skin, but their thumb won't move. And they have to keep increasing that amount of energy slowly until a certain point is reached, and their thumb will always move when that shock is delivered. But anything less than that, even if you send it kind of fast and furious, your thumb's not going to move. That point at which they were able to get their thumb to move, when they had given enough energy to the thumb, enough of an electrical stimulus to the muscles of the thumb to get it to move the thumb, that's called threshold stimulus. Whatever that voltage is called threshold stimulus, and that's represented here. See, a small amount of energy wasn't able to recruit motor nerve fibers. A little bit more, still not enough. Finally, You have enough to cause one muscle fiber in this hypothetical muscle to contract, so you have a contraction. As you increase the energy, the voltage, you will get stronger twitches. Eventually, once you crank up that energy enough, every muscle fiber that can be brought in to help, that can be recruited, will be recruited. And at that point, it doesn't matter how much more energy you send to that muscle, it can only contract so much. Everything that can be recruited has been recruited, and the strength of your contraction will not increase. It will eventually decrease with fatigue, but that's its own separate thing. So far, we've been talking about these discrete, separate electrical events. You send an electrical signal, a zap, and your muscle twitches. And then you wait. And you send a new zap, and your muscle twitches again. And then you wait. Everything goes back to normal in between. Each one of those contraction events coupled with an electrical firing is referred to as a twitch. And on a graph, it looks like this, where you have a contraction, and then it goes back to baseline. Contraction, and then goes back to baseline. If you fire electrical signals fast enough, you can build their strength on top of one another. So you send an electrical zap to the muscle. It stimulates the muscle to contract, but before it gets a chance to fully relax, you send another zap. And so it contracts again, only this time its baseline is higher. So the force of that contraction ultimately results in the force of that change will ultimately result in a stronger contraction. More muscle fibers will be recruited than if you would have done that as two separate electrical events. This is called summation, where you have one stimulus that's building off the other. Now, how that works is, remember, you have that action potential that's going down the length of the sarcolemma. This set of channels is stimulated first. You have depolarization. That's going to stimulate the next set of channels to depolarize. And in the meantime, this one tries to put things back to normal, back to how it was before. That'll go back to normal fairly quickly. By now, your signal's zapped down several channels away. If you send another signal now, this can depolarize again, while this one down here is in the process of depolarizing. If you send them fast enough, you can have lots of twitches, or even a sustained twitch that builds on top of each other or just seems to be held. So you have a stimulus that causes a contraction. You let it go all the way back to relaxation before another contraction event happens. That's referred to as a twitch. When you have a contraction that builds on another contraction, that's summation. You need to have some amount of relaxation in between, just incomplete relaxation, for it to be considered summation. If you send your electrical signals so fast and furious that the muscle never gets a chance to relax, that's called tetanus. Fused tetanus, to be precise. You don't really experience this typically in your body under normal conditions. This physiological phenomenon is called tetanus, and the disease is named after this phenomenon. Okay, so don't think that every time I refer to tetanus in lecture, on tests, whatever, that I'm referring to a disease-induced state. I'm referring to a muscle contraction that holds strong and doesn't relax, unless you hear otherwise. Okay? The disease causes this tetanus state, and so you call it the disease tetanus, but tetanus in and of itself is not a disease. Now, eventually, you're going to fatigue, and so the muscle is going to lose its contractile force. Fatigue prevents muscles from contracting indefinitely and reduces the effectiveness of muscle until the fatigue subsides. And this comes down relatively slowly, okay? And until you get more or less down close to baseline relaxation again, you're not going to be able to induce the same strength of contraction. The mechanisms behind this are complicated and actually more unclear than you might otherwise expect. But in summation, remember 3 distinct types of contraction events. A twitch, where you go from relaxation to contraction to relaxation. A summation event, where you go from relaxation to contraction to partial relaxation to more contraction. And tetanus, not the disease, the physiological state, where you have relaxation in the beginning, then contraction, and you don't get an opportunity to relax again because the next stimulus comes in too fast. You have contraction, 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 until you're at maximum and you hold there.